Periodic motion question 9. The diagram is showing the apparatus for investigating forced vibrations and resonance of a mass spring system. The graph shows displacement against time when the system is resonating. State what is meant by a forced vibration. So this is a little bit like a definition question. So you need to point out that the system is made to oscillate by a periodic external force. Alternatively, you might say another oscillator is forcing the system to vibrate. The two words that I've highlighted were essential requirements on the mark scheme, so not enough to say oscillate by an external force. You need the idea of it being a periodic force. Next, under what condition will resonance occur? Well, resonance always occurs when a driving frequency equals a natural frequency. You just have to match that general description to the specific situation that we have in front of us here. So the driving frequency is the frequency of the wheel or the motor, and the natural frequency is the natural frequency of the mass spring system. Next, you're told the spring constant of the spring within the experiment is 9 newtons per metre, and you're asked to use information from figure 2 to find the value of the mass. So looking back at figure 2, we have a displacement time graph. So from this graph we can determine the time period of the oscillation. Note this label of 3 that I've added corresponds to the end of the graph paper here. So reading the time period, you could try and look at the time for one oscillation, which is to this point here, or you might find it easier to look at 2 full oscillations. 2 full oscillations appear to correspond to 2.5 seconds, so you could then halve that to 1.25 seconds for one oscillation. So having measured the time period from the graph, you can now use the equation for the time period of a mass spring system, which you would find on the data sheet. We're trying to find mass, so it makes sense to square both sides of the equation and rearrange for mass. Finally, substitute the spring constant provided, the time period you've read from the graph, and the constant for pi squared. And last step, I've chosen to give my answer to 2 significant figures. Next, we look at the final part of the question. When the rotating wheel stops, this graph is showing how the amplitude of the oscillations of the mass varies with time. You are asked to explain whether this graph supports the suggestion that the amplitude varies exponentially. You must also show your reasoning clearly. So you need to understand what is meant by the term exponential and be able to apply this to the graph. When you have an exponential decay, it means that the value, in this case for amplitude, must fall by the same factor for any given time interval. So I've chosen to look at the amplitude falling by a factor of 1/2, so falling from 10 to 5 centimetres, and I've marked on the graph to show that that takes a time of 20 seconds. I've then repeated the process, looking at the amplitude halving once more from 5 centimetres down to 2.5. And once again, this corresponds to a time interval of 20 seconds. So finally, just stating my argument clearly, the time to half is the same, or is always a constant, and this suggests that this is indeed exponential decay. Note, you don't have to use halving, it could be any factor that you choose. Lastly, you're asked to find the ratio of the energy of the oscillator after 20 oscillations to the energy of the oscillator at a time equal to 0. So consider then the time corresponding to 20 oscillations. We measured the time period as 1.25 seconds in the original graph. So 20 oscillations corresponds to 25 seconds. The amplitude at 25 seconds can be found from the graph. So looking at the graph here and reading for 25 seconds, up here we can find a value for the amplitude, which I've read as 4 centimetres. Why have I taken that reading? It's because I know that energy is proportional to amplitude squared. So the ratio of the two energy values will be equal to the ratio of the two amplitudes squared. So here I have the amplitude after 20 seconds, 4, which I have squared, and I'm dividing that by the amplitude at time equals 0, which was 10 centimetres as shown on the graph, once again squared. This leads me to a final answer of 0.16.